This is going to be the last part of Chapter 13, and we're going to be reviewing just a little bit on what we did with single substituents already present on the benzene ring and how that affects where a second substituent will go, and then we're going to look at multiple substituents on the molecule. So this is just a quick review. So up here it's just telling us that these are strongly activating groups, so they're going to be orthopair directors. If you have your phenol then, and you're reacting at doing a nitration, then your nitro group is going to go ortho and para in its position. If you have something along this lines, which is a acyl chloride, it's a meta-director, so when you undergo, in this particular case, your your halogenation of your benzene ring, then you're going to put your chlorine, in this case, in the meta position. So we're going to skip on over to looking at multiple substituents. So if we already have two substituents here, we have two methyl groups. Both of these are orthopair directors. So it really doesn't matter what I do, because if I put it here or here, it's ortho to this compound, or this part of the compound, or here and here, it's ortho to this part, and it's going to be equal regardless. Now this, of course, is the acid anhydride, so you're going to break your structure here, use your aluminum chloride as its part of the reaction, and then this is what's going to attach onto the molecule in an ortho position. So you could have put it here, you could have put it here, here, or here, and it'd all be equal. Now if you have something along this lines, the top you have a methyl group, which is an orthopair director, and the bottom you have a nitro group, which is a meta-director. If you can satisfy both of the groups that are present, that's what you will do. So obviously you can't put anything para because something is already para here. So this bromine is going to go ortho to our methyl group, which will also make it meta to the nitro group, both being satisfied. If you have to make a decision between what things go where, then whatever is the more strongly activating substituent takes precedence over anything else. So basically look at the chart. The higher it is on the chart, the more strongly activating, that takes precedence over a group that's below it somewhere. So if there's not equal positioning, then you'll have to go by that particular method. So if we're looking at this one, for example, this is a very strong activating substance. It's got the nitrogen. The chlorine is actually a deactivating, but it's going to be an orthopair director as well. So instead of it being ortho to the chlorine, because chlorine is much farther down on the chart and a less of an activator, then it's going to be ortho to this functional group on top, and this will be our major product. Now in a situation like this, both of these are alkyl groups. Since they're both alkyl groups, you want to look to see if there's any steric hindrance that might take place. So since you have this really large tertiary butyl group here, if I try to put something ortho here, it's going to have a lot of steric hindrance with that big group. But here, up here by the methyl, it's not. So therefore, our NO2 group is going to come up here by our methyl. In this particular case, we have two methyl groups again. Neither one is dominant over the other, but if you put something here in the ortho position, then you've got some steric hindrance. It's not quite as stable in that position. So if we put it here, that will be more stable. It will be ortho to this methyl group. It'll be para to this methyl group. If we put it here, it will be ortho to this methyl group and para to this methyl group, so either one of those will be equally efficient. Now this is a really important statement, because when we start doing synthesis types of reactions, there are some things that cannot take place once you put a very strong deactivating substance on the reaction. So strongly deactivated structures do not allow for the Friedel-Crafts acylation or alkylation to take place. And these are our strong deactivating structures that we talked about on our chart earlier. So make sure you have that chart available and can look at it to see what our strong deactivators are. So in other words, if I do a nitration first, or if I do a sulfonation first, since we recognize those functional groups, then we cannot do a Friedel-Crafts alkylation or a Friedel-Crafts acylation afterward. So there is going to depend on what's already present as to whether or not a particular reaction can take place. So let's look at some synthesis types of reactions. So in this particular one, I want to synthesize a meta-bromo-acetophenone. So this is a bromo group that I'm going to put on by a halogenation process. This is your acetophenone group, and I'm going to put this one on by a Friedel-Crafts acylation. Which of these is a meta director? Because that's what I want to do, is have them in meta position. This one, remember, even though it's deactivating, is an ortho-para director. So if I put this on first, then this functional group will either go ortho to it or para to it, which is not what I'm looking for. So if I put this one on first, it is a meta director, therefore my bromine will go in the meta position as it should. So the next couple slides just show you the attachment of these two things. So the first one is we do a Friedel-Crafts acylation. You can use a acetyl chloride, or you can use this acid anhydride. Either one works, doesn't matter. You'll put on this functional group first, and then we'll do a halogenation using the bromine. And you can use your aluminum chloride, you can use your iron 3 chloride, iron 3 bromide, either one, any of those would be acceptable to put that bromine on. Now if I want to make let's go back and see if we can make a para version of that same compound. So if we want to make the para version of a bromoacetophenone, remember our bromo group is going to be ortho-para directing. Our acetophenone group is going to be meta-directing. So in this particular case, I'm going to have to do the halogenation first. It doesn't really matter where you put that. And then we're going to do our Friedel-Crafts acylation. So I'm just going to use this, it's a little bit smaller to make it easier to stick on here. And since this is an ortho-para director, then I'm going to break here and add this in the para position. So the order definitely matters in this particular case as to where I'm going to be able to put my functional groups. Now let's look at this one. I want to make a meta-nitroacetophenone. This is a very strong deactivating. So remember, if I put this on first, I cannot do a Friedel-Crafts acylation or alkylation. Both of these are meta-directors, so it really doesn't matter which one goes on first, except for that rule that we can't carry out those two processes. So I'm going to have to do my Friedel-Crafts acylation first, and then I can do my nitration second. The other way, the reaction will not take place. So here's our Friedel-Crafts acylation using our acetic anhydride. Here is our first product, or our acetophenone, and then we're going to do our nitration using our nitric acid in the presence of sulfuric acid, and it'll go on the meta group. Now if we're doing this particular one, we're making para-nitrobenzoic acid from toluene. Toluene, remember, is an orthopara director. If I want my nitro to go in the para position, then I'm going to do the nitration first. And then if I would like to get rid of this methyl group, I can change my methyl group into a carboxylic acid group using an oxidation process. So let's see how that one works. So here's my methyl group. I'll do my nitration first so that it goes in the para position. And then I'm going to do an oxidation using this of course remember is our chromic acid combination. So this could be potassium dichromate or sodium dichromate, sulfuric acid, water and heat. And this is going to convert this benzylic carbon into a carboxylic acid. Remember, as long as there are benzylic hydrogens, then you can carry out this oxidation process. So try some of the reactions that are in your practice problems, because those will be important to be able to do some of these synthesis reactions. The last thing we're going to look at are substitutions on naphthalene. Remember, naphthalene is a bicyclic type of structure that has two benzene rings attached. Your only positions for electrophilic aromatic substitution are going to be carbons 1 and 2, because anywhere else you put it, it's going to be 1 and 2. So like this will be 1, that would be 2. This would be 1, that would be 2. This would be 1, that would be 2. So just depending on how you're numbering it. So the only two sites on which you can put something is on carbons 1 and 2. And just to determine which is faster, the carbon 1 group is going to take place faster than at the carbon 2 group. So you should get a major product from the carbon 1 group being attached, and then the carbon 2 group would be a second. So you can see it's much lower percentage, like about 10% in comparison to 90%.